Okay, so have you ever heard about something that sounds like, I don't know, straight out of Star Trek or something? Like, it's so futuristic it seems impossible. But then you realize, wait, it's actually happening right now.
Yeah, I know that feeling.
That's quantum computing for me, honestly. Like, it's totally mind-bending. Forget about computers as we know them, just simple on and off switches.
Right.
Quantum computing is tapping into this, like, fundamental weirdness of the universe.
Yeah.
We're talking about things like wave-particle duality, superposition.
Entanglement,
exactly.
No.
To solve problems that would make our current, like, most powerful supercomputers just go, nope, I'm out.
Right. Yeah, it's pretty incredible.
It's mind-blowing. And I'm sure you're all as intrigued as I am to really get into this, so let's dive in.
Absolutely. And the thing is, this isn't some far-off technology. This is happening now. It's already actively transforming research. And that's what we're going to look at today. Specifically, we're taking a deep dive into how quantum computing is shaping up to, well, completely reshape various sectors in the coming decades.
It really is.
And to guide our exploration, we have this really fascinating article called Transforming Research with Quantum Computing.
And that's exactly what we're aiming for today.
Yeah.
To cut through all the complexity, all the jargon.
Yeah, it can be a lot.
It can be really dense.
Mm-hmm.
And we want to pull out the truly significant insights from this research.
Right.
To highlight the game-changing potential, the real, groundbreaking applications of this quantum technology without getting too bogged down, I think, in those overly technical details that can sometimes make your eyes glaze over.
Yeah, we'll try to keep it straightforward.
So consider this your express lane to understanding the next big leap in pretty much everything, really.
Yeah, and I think this article does a really good job of laying out, the path forward. So we'll be walking through some of its main arguments, discoveries, all that, just to give you a clearer picture of what this future might look like.
Exactly. Okay, so let's unpack this idea of the quantum era. What does that even mean? For those of us, who don't live in quantum physics labs, what's the fundamental difference between the computers we use every day, our laptops, our phones, and these quantum powerhouses that we're talking about? What's at the core of that difference?
Well, you have to start with the most basic building block of information. So with our everyday computers, it's the bit. And bits are like a light switch. They're either on, 1, or off, 0. Very straightforward.
Yeah, classic binary.
Exactly. But quantum computers use qubits. And these qubits, well, think of them more like a dimmer switch. It's not just on or off. It can be anywhere in between, any level of brightness.
Ah. Okay.
And that in-between state, that's what we call superposition. A qubit can exist in multiple states, both 0 and 1 at the same time. And this ability to be in multiple states at once is what gives a quantum computer this, massive advantage. It can explore exponentially more possibilities than a classical bit that's stuck with just one state at a time.
Right.
Imagine searching a library. Instead of checking each book one by one, you could somehow check every single book all at once. That's the power we're talking about here.
So it's not just one or the other. It's like a blurry in-between state of both.
Yeah, exactly. A bit of a fuzzy combination. And that's already a huge difference in how they can approach problems.
It is. It is. So we have these qubits. They're in this weird, blurry state. But then it gets even weirder, right?
Yeah.
Because then there's this thing called entanglement.
Right. Now, with entanglement, imagine you've got two of those dimmer switches. They're physically separated. Maybe they're even miles apart. But somehow they're linked so that if you adjust one, make it brighter or dimmer, the other one instantly mirrors that change.
No matter how far apart they are.
No matter how far apart they are. It's like they're connected by some invisible force. So if you measure the state of one entangled qubit, you instantly know the state of the other one.
So they're like twins almost.
Yeah.
But separated by potentially huge distances.
Exactly, like quantum twins. And the article mentioned that this entanglement, it leads to what they call an enormous expansion of the parameter space.
Okay, break that down for me a little bit. Parameter space.
Sure. So in simpler terms, it means that they can consider a vastly larger number of possibilities all at the same time. It's like having, an exponentially bigger playground to explore and to find solutions.
Ah, okay. So we've got superposition, the blurry state, and then entanglement, the spooky action at a distance. Combined, they create this, massively expanded space of possibilities for quantum computers to work with.
Exactly. Think about a really complex problem, like finding the best delivery route for hundreds of trucks across a city.
Yeah.
A classical computer would have to check every single possible route one at a time, which could take forever. But entangled qubits working in superposition, they can explore so many of those routes simultaneously,
Oh, okay.
which just drastically speeds up the process of finding the best solution.
Wow. Okay, so that's the potential power. But then in the article, you mentioned this challenge called decoherence.
Right, right. And that word sounds a bit ominous, doesn't it?
It does. Not a good thing, it sounds like.
No, not really. It's a major obstacle. You see, these quantum states, the superposition and the entanglement, they're incredibly fragile.
Really?
Yeah, when qubits interact with the outside world, even in the tiniest ways, like stray electromagnetic fields, vibrations, temperature changes, they can lose their quantum properties. It's kind of like, remember our dimmer switch analogy? Decoherence would be like bumping that dimmer and it suddenly just flickers and then settles randomly on or fully off. It loses that valuable in-between state.
Ah, okay. So that's like a glitch in the matrix almost.
Yeah, kind of. And it's a big one. It's one of the biggest obstacles to building larger, more stable quantum computers.
Right, right. So you got to shield these quantum states from the environment.
Yeah.
Keep them totally isolated to avoid decoherence.
Exactly. It's a massive engineering challenge.
Okay. So the article talks about this speed advantage that quantum computers have. Are they just like super fast versions of our current computers?
Yeah.
Can I like finally download a movie in 2 seconds?
Well, not exactly. For your everyday tasks, browsing the web, sending emails, writing a document.
Watching cat videos.
Exactly. Watching cat videos. Your laptop or phone is probably going to be just as fast, if not faster. The real power of quantum computing, it comes into play when we're dealing with problems of immense complexity, like problems with a staggering number of possibilities. And that's where that speed advantage becomes truly revolutionary.
So it's not just about doing the same calculations faster, but about tackling problems in a fundamentally different way. Okay, so let's get specific here. The article highlighted a few sectors, where this speed advantage is really going to make a difference in the coming years. Defense, finance, chemistry, drug discovery, cryptography. Can you maybe unpack one of those? Give us a concrete example of this speed up in action.
Sure. The article talks about this algorithm called Grover's search algorithm.
Grover's search algorithm, okay.
Yeah. Imagine you're looking for a single specific grain of sand on every beach in the world.
That's a lot of sand.
That's a lot of sand, right? A classical computer, essentially, would have to check each grain one by one.
That's going to take a while.
It's going to take a very, very long time. But Grover's algorithm, it provides what they call a quadratic speedup for this type of unstructured search problem. Now, it wouldn't find that grain instantly, but it would drastically reduce the number of grains you'd have to check.
Oh, okay.
So it makes the task, well, maybe not easy, but at least feasible in a reasonable amount of time.
Okay, so it's about tackling problems that were previously considered impossible. Not just about doing things faster, but about doing things that we simply couldn't do before.
Exactly.
So this leads to, like you said, enhanced data analysis. Being able to process these incredibly complex problems, maybe all at the same time, and overall just faster computation for these very specific, really tough challenges.
Right. And the exciting thing is, this isn't just theoretical anymore. Quantum technology is already being used in some real-world applications, even at this early stage.
Oh, really?
Yeah. Like, there are people trying to break modern encryption using quantum computers.
Wow.
And there's a lot of work being done on using quantum computers to model really complex systems.
So there's a bit of an arms race going on here.
Yeah, you could say that.
Yeah.
It's a race to see who can harness this power first. And that brings us to security. I mean, if quantum computers can potentially crack our current encryption, that sounds like a huge problem,
It does.
right? A major vulnerability.
Yeah.
And the article talks about the development of post-quantum cryptography, which is essentially building new encryption techniques that would be resistant to quantum attacks.
So it's like building a new kind of lock for our digital information, knowing that the old locks might not hold up against these new quantum keys, so to speak.
Exactly. It's about getting ahead of the curve and making sure our data stays secure, even in a world with powerful quantum computers.
Right. Okay, so moving on, the article talks about quantum supremacy. That sounds like a really big deal. What does that even mean?
So quantum supremacy, think of it as the point where a quantum computer can do something, complete a specific task that even the most powerful classical supercomputer just couldn't do, at least not in a practical time frame. So it's not about quantum computers being universally better than classical computers at everything.
Right.
It's about demonstrating their superior power for a particular type of problem.
Got it.
Like, imagine a race between a horse and a car. The car is obviously faster over long distances, but the horse might be quicker off the starting line.
Oh,
So it's about each one having an advantage in different situations.
right. Okay, that makes sense. And the article mentions that some big players like IBM and Google are really going after this quantum supremacy.
They are. They see it as the key to revolutionizing fields like, as we talked about, encryption, but also drug discovery, material science. And there's been a lot of progress. The article even mentioned a claimed instance of quantum supremacy.
Really?
Yeah, where a quantum computer performed a specific calculation millions of times faster than the best classical computers could.
Wow.
It was a specialized problem for sure, but it was a major proof of concept.
Right. It shows that it's possible.
Exactly.
Okay, so what's driving this incredibly rapid progress in quantum computing? Why is this all happening now?
Well, I think there are a few reasons. First of all, the problems we're trying to solve are getting really, really complex. We need more powerful tools. Think about things like understanding complex chemical reactions or optimizing these huge global supply chains, or building even more sophisticated financial models. All of these are pushing classical computing to its limits.
That makes sense.
And quantum computing, with its ability to handle massive amounts of data, explore multiple possibilities at the same time, it has the potential to provide much faster, more effective solutions for these challenges.
Okay, so the problems are getting bigger, more complex. We need new tools.
Exactly. And then there's this whole idea of accessibility.
Right.
Cloud-based quantum computing is really a game changer here.
How so?
Well, it's lowering the barrier to entry for people to experiment with quantum computing. Now, you don't need to spend millions of dollars to build your own quantum computer. Startups, researchers, even large companies, they can access these systems through the cloud and experiment with quantum algorithms.
That's huge.
It's democratizing access to this technology, and that's leading to a wider range of applications being explored, from agriculture to telecommunications to transportation. It's really exciting.
Yeah, absolutely. Okay, the article also had this kind of intimidating phrase, impassable nonlinear equations. What's that all about?
So that one is a bit technical, but essentially it's about the limitations of traditional computers in dealing with problems where things aren't straightforward. The relationship between different factors is not a simple straight line.
Okay.
Think about predicting the weather or modeling the flow of fluids. These are complex nonlinear problems, and quantum technology is much better equipped to handle these types of complex operations.
So traditional computers struggle with the messiness of the real world.
Yeah, in a way. And that's why quantum computing is so exciting for fields like climate modeling, even things like air traffic control. It's about being able to tackle these really complex systems that don't behave in a simple, predictable way.
Okay, so we may not have these like fully realized large-scale quantum computers everywhere yet, but the article talked about all these pioneering applications that are already being explored. So even though the technology is still developing, people are already finding ways to use it.
Exactly. And there's a lot of excitement around this.
Yeah, well, let's get into some of these applications.
Sure.
Let's start with data security.
Okay.
This is something that I think a lot of people are concerned about, especially with the potential for quantum computers to break our current encryption methods.
Right. And that's why there's this big push for quantum-resistant cryptography. It's about developing new ways to protect our information, knowing that the old ways might not be enough in the future.
So it's about staying one step ahead of the bad guys, so to speak.
Exactly. The article mentioned things like quantum key distribution.
Quantum key distribution.
Yeah. This is a way to create encryption keys that are virtually impossible to crack, even with a quantum computer.
So even if quantum computers can break our current codes, we'll have new unbreakable codes ready to go.
That's the idea. It's about anticipating the threat and building defenses in advance.
Wow, okay. So we've got data security. What about artificial intelligence? The article mentioned this idea of boosting AI with quantum computing.
Right. This is one of the most exciting areas.
Yeah.
Quantum computers, with their ability to be in multiple states at once, they could potentially supercharge certain aspects of AI. Like, imagine tasks that currently take classical computers a very long time, like training complex AI models. Quantum computers might be able to do those tasks much, much faster.
Interesting.
And this could lead to breakthroughs in all sorts of areas.
Cloudcast.
Oh, better encryption, more accurate financial models, even discovering new materials, advancing healthcare. There's a lot of potential here.
So it's about using quantum to push the boundaries of what's possible with AI.
Exactly. The article highlighted the ability of quantum computers to identify patterns and correlations in data. This is something that's really important for many AI algorithms.
Right. Okay. So we've got data security, AI. Now, this one surprised me a bit. The article mentioned quantum computers being used to help with something as ordinary as urban traffic flow.
Yeah, no, it sounds a little strange at first. But think about it. Traffic optimization is a really complex problem. There are so many variables, so many moving parts.
Right.
And quantum computing could potentially help us find much more efficient solutions. Like the article gave this example of Volkswagen.
Okay.
They're already using early-stage quantum algorithms to try to manage traffic congestion in some big cities.
Wow.
And even with electric vehicles becoming more common, optimizing traffic flow is still crucial for reducing emissions, making cities more livable.
Absolutely.
And quantum computing could be a big part of that.
It really feels like with quantum computing, we're not just talking about faster computers. We're talking about a different way of thinking about problems, a different way of approaching them.
Yeah, I think that's a great way to put it. It's a whole new paradigm.
Okay, so let's move on to another really important topic, climate change. Right. The article talks about how quantum computers could help with climate prediction.
Right, because climate models are incredibly complex.
They are.
And they require immense amounts of computing power, which limits their accuracy.
Right, right.
But there's a lot of hope that quantum computers could change that. Organizations like the UK Met Office, they believe that quantum computers could enable these, super advanced climate models that could give us much more accurate predictions.
So we could potentially forecast extreme weather events more accurately, understand long-term climate trends better.
Exactly. And ultimately be better prepared to adapt to climate change.
So from city traffic to global climate models, it's amazing the range of problems that quantum computing could potentially help us address.
Yeah, the potential is vast. And it's not just about predicting the future, it's also about shaping it. Like the article talks about designing cutting-edge medicines.
Okay, tell me more about that.
So, discovering and developing new drugs is a very long, expensive process. But quantum computers have the potential to significantly speed that up.
How so?
Well, they could help us model the behavior of molecules with much greater accuracy.
So we could understand how different drugs might interact with the body, potentially before we even start testing them in a lab.
Exactly. We could design more effective and targeted therapies. The article even mentioned a company, Protein Core, that's using quantum computing for protein modeling in drug development.
Wow.
And their goal is to develop better treatments for things like cancer and heart disease.
That's incredible. It really feels like quantum computing could touch every aspect of our lives in some way in the future.
I think so, too. It's a technology with a truly massive scope.
So across all these different areas, there's obviously a lot of technological innovation happening.
Oh, absolutely. And the article touched on some of the research that's pushing quantum computing forward. It's not just about building the computers themselves, it's also about developing the software, the algorithms, and all the supporting technologies.
Yeah.
And the goal is to really go beyond what even the most powerful supercomputers can do today.
And it's not just academic institutions working on this. The article listed some of the biggest names in tech: IBM, Microsoft, Google, Intel, even companies like Qubits and ZTE.
Right, and then you have these smaller innovative startups like D-Wave, Rigetti, IonQ, all making big investments. It's like a global race to unlock this potential.
Absolutely.
Yeah.
Yet alongside the hardware development, the article also highlighted the advances in quantum programming languages and the creation of more efficient quantum algorithms.
Yes, that's crucial. You need the right software to tell the hardware what to do.
Exactly. So the article dives into these software tools and platforms for quantum programming. And it sounds like these tools are really important for making quantum computing more accessible to a wider range of developers.
Absolutely. These tools aim to simplify the process of creating and using quantum algorithms. So you don't need to be a quantum physics expert to start experimenting with this technology.
That's a good thing, because I am definitely not a quantum physics expert.
Right. Well, the article even included a figure 3, that showed some of the key platforms that are available.
Okay, can you just walk us through some of these tools for those who are just listening?
Sure. So there's Qiskit from IBM, a really popular Python-based tool that lets developers build and run quantum programs on IBM's quantum computers. Then there's QSharp from Microsoft, which provides libraries and tools for debugging and simulating quantum code. Google has Cirq, which is designed specifically for working with these early-stage quantum computers that are still prone to errors.
Right.
And then you have PyQuil from Rigetti Computing, which uses their specific quantum language. And more recently, there's Silk from ETH Zurich, another Python-based language that focuses on making sure the code is safe and correct.
Okay, so a lot of different options, but all with the same goal, to make quantum programming easier.
Exactly. And then there's TKET from Quantinuum, which is a really comprehensive toolkit, and iQuantum Simulator from the University of Melbourne, which helps you use quantum resources from different providers.
Wow, that's a lot to keep track of. It sounds like the quantum software ecosystem is growing really quickly.
It is.
Yeah.
And along with these specific tools, there's this growing trend of cloud-based access to quantum resources.
Right, you mentioned that earlier.
Yeah. Platforms like IBM Quantum Experience, Microsoft Azure Quantum, and Amazon Bracket are providing access to quantum computers and simulators through the cloud.
So instead of having to buy your own expensive quantum computer, you can just rent time on one.
Exactly. And that makes it much easier for researchers, businesses, even individuals to start experimenting with quantum computing.
Okay, so that's really lowering the barrier to entry, driving innovation.
Yeah.
But the article also mentioned some open challenges of quantum software engineering, so it's not all smooth sailing on the software side, right?
Yeah. Definitely not. There are some big hurdles to overcome.
Like what?
Well, one challenge is the risk of getting locked into a specific vendor's platform. You know, like, what if you build your application using one company's tools, and then later you want to switch to a different provider?
Right, that could be a problem.
Yeah. And then there's the whole issue of quantum circuit design. It's really complex. It's very different from traditional software development.
So it's like trying to build a house using tools and materials that you've never seen before.
Exactly. And then you have this issue of compatibility. Different tools are based on different languages, different architectures, so it can be hard to get them to work together.
So a lot of challenges, but also a lot of opportunities.
Absolutely. It's a very young field, but it's moving incredibly fast.
Now, the article shifts gears a bit and talks about unlock the future, the transformative capabilities of quantum computing. And there's a figure 4, that lists a whole bunch of potential ways that quantum computing could impact research. So let's go through some of these, starting with quantum simulations.
Okay, so this is one area where quantum computers are expected to have a huge impact. They have the potential to simulate the behavior of complex molecules much more accurately than classical computers.
Why is that so important?
Well, understanding how molecules behave at the atomic level is crucial for all sorts of things, like discovering new drugs or designing new materials.
Right.
Current computers struggle to simulate these interactions accurately because they're so complex. But quantum computers could potentially overcome this limitation, and that would be a game changer for fields like drug discovery and material science.
So we could design new drugs more quickly, create new materials with specific properties?
Exactly. It could really accelerate the pace of scientific discovery.
That's exciting. And then the article talks about commercialization. How is this transition from research to real-world applications happening?
Well, we're starting to see a lot of activity in this area. Both large companies and smaller startups are exploring ways to commercialize quantum technology.
Okay.
And the rise of cloud-based quantum computing is making this much easier. Businesses can now experiment with quantum applications without having to invest in their own expensive hardware.
Right.
So it's opening up all sorts of new possibilities.
So it's about finding practical uses for this technology, making it accessible to businesses.
Exactly. And the article suggests that businesses should be thinking about this now, about how they can partner with quantum computing companies to take advantage of this new technology.
It sounds like a lot of opportunity for early adopters.
Yeah, definitely. Okay, so moving on. The article talks about this idea of quantum-inspired optimization. Now, what is that?
Yeah, that one sounds a little cryptic.
So it's about taking some of the ideas from quantum computing, specifically from quantum algorithms, and applying them to traditional algorithms to solve optimization problems.
Hmm.
So optimization problems are basically problems where you're trying to find the best possible solution out of a huge number of options, like finding the most efficient delivery route or managing a complex financial portfolio.
Right, right.
And even without a full-blown quantum computer, these quantum-inspired techniques can often lead to better solutions.
That's fascinating. So it's like taking inspiration from the quantum world to improve our classical methods.
Exactly. It's about finding ways to get the benefits of quantum thinking without needing the full power of a quantum computer.
Okay. The article also talks about the potential impact of quantum computing on robotics. How would that work?
Well, robotics often involves a lot of complex calculations, especially for things like planning movements, controlling robots, and processing sensory data.
Right.
And quantum computers, with their speed and ability to handle complex problems, could potentially make robots much more intelligent and capable.
So we can have robots that can perform surgery more precisely, or autonomous vehicles that can navigate more safely, or even robots that can work in hazardous environments.
Exactly. And the article even mentioned the idea of robots using cloud-based quantum computing resources to solve complex problems in real time. Like, imagine a group of robots working together in a factory, all coordinated by a quantum computer in the cloud.
Wow, that's some next-level automation.
It is. It's about pushing the boundaries of what robots can do.
Okay. And then we have quantum AI, which we touched on earlier. How could quantum computing really transform the field of artificial intelligence?
Well, one of the biggest potential impacts is in the area of quantum machine learning. Quantum computers could potentially accelerate the training of AI models, leading to more powerful and efficient AI systems.
So we could have AI that can learn faster, solve more complex problems, make better decisions.
Exactly. And the article mentions some specific areas where this could have a big impact.
Like what?
Like autonomous driving, for example. Self-driving cars rely on these complex neural networks to process data from sensors and make decisions about navigation. And quantum computers could potentially make those neural networks much more efficient, leading to safer and more reliable autonomous vehicles.
Okay.
There are also a lot of research efforts going on at companies like NASA, JDAI, and Baidu, exploring the possibilities of quantum AI.
So it's still early days, but the potential is huge.
Absolutely.
Now, the article brought up this topic that I hadn't really thought about before, quantum sustainability. What's the connection between quantum computing and sustainability?
So this is a really important consideration. Quantum computers require a lot of energy to operate, especially to keep the qubits at these extremely low temperatures. And as quantum computers become more powerful, their energy consumption is likely to increase.
So it's a bit of a trade-off. We get this incredible processing power, but at a potentially high energy cost.
Exactly. And that's why researchers are looking at ways to make quantum computing more energy efficient.
So building more sustainable quantum computers will be crucial for their long-term viability.
Absolutely. Okay, so let's move on to quantum-safe networking and cybersecurity, which brings us back to that issue of encryption we talked about earlier.
Right. So it's not just about quantum computers breaking our current codes. It's also about creating new codes that are resistant to quantum attacks.
Exactly. Quantum-safe networking is about building a more secure digital infrastructure for the future.
So things like quantum key distribution, which we talked about before, would be a part of this.
Right. That and other techniques like lattice-based encryption, which are designed to be resistant to attacks from even the most powerful quantum computers.
So it's a whole new approach to cybersecurity.
It is. It's about anticipating the threats of the future and building defenses now.
Okay. And the article also touched on data mobility and big data analytics, which seems like a natural fit for quantum computing.
It does. Quantum computers can process and analyze massive data sets much faster than classical computers, which could revolutionize big data analytics.
So we could extract more insights from the data we're already collecting, make better predictions, make more informed decisions.
Exactly. And the article specifically mentioned the potential for this in the context of transportation. Like, imagine being able to optimize traffic flow in real time based on data from millions of vehicles.
That would be incredible. And then there's the broader topic of intelligent transportation, which goes beyond just optimizing traffic.
Right. Quantum computing could potentially help us solve a whole range of transportation challenges, like reducing emissions, making transportation more efficient. and even creating new forms of transportation.
Wow.
The article talked about things like quantum sensors that could improve traffic management and quantum-enhanced navigation systems that could reduce congestion.
So potentially a whole new era of transportation powered by quantum computing.
Absolutely.
Okay, and then we have quantum cloud computing, which you explained earlier is about making quantum computing resources more accessible.
Right. So instead of needing to buy and maintain your own quantum computer, you can access these resources through the cloud on demand.
And that's really lowering the barrier to entry for researchers and businesses, right?
Exactly. It's democratizing access to this technology, and it's also making it easier to scale up quantum computing applications.
Okay. And finally, we have resilient quantum computation. What's that about?
So this is about addressing the fact that quantum computers are still very sensitive to errors.
Right. We talked about that earlier with decoherence.
Exactly. So resilient quantum computation is about developing techniques to make quantum computers more reliable, more fault tolerant. It's about making sure that they can perform complex calculations accurately, even in the presence of noise and errors.
So it's about making these powerful computers more robust, more dependable.
Exactly.
Okay. So the article concludes by talking about revolutionize the world, moving target for quantum advantage.
Right. And I think that's a really important point. Quantum computing is a rapidly evolving field. What we know today might be completely different tomorrow.
So we're just at the beginning of this quantum revolution.
Exactly. And the article emphasizes that even though corporations are getting more involved, the fundamental research being done by academics is still incredibly important.
It's about pushing the boundaries of what's possible, exploring the unknown.
Absolutely.
Well, this has been an absolutely fascinating deep dive into the world of quantum computing. It's clear that this technology has the potential to revolutionize research and transform industries in ways that we can barely